This module examines the concept of forecasting and its use in budgeting. The first group of forecasting techniques are very practical and not technical. The naive approach uses last year's value and moves it forward. No new information is added. Some might say it's a conservative forecast because it assumes what happened last year will be repeated. That may work if nothing is changed. In the judgmental approach, typically, something changed other than time. Last year may have been a great year unlike those before. Maybe it's best not to expect another great year. So you use your judgment and estimate a lower budget. A third, non-statistical approach is to use a group forecasting exercise. You invite in a group of experts and have them try to come to a consensus. Who might you invite for the small group? You might convene a group of managers from other laboratories to discuss their projections of future services. Or it could be more high level and include economists, health experts, epidemiologists, business leaders, or others. The number and their background would vary by the nature of the forecast expected. Short of a consensus, you at least end up with a basis upon which to step out with your own forecast. A simple method is to use what's called a deterministic formula. That's one where you know the future value of the items that are multiplied together. Several examples help illustrate this point. The tax rate times the tax base equals the tax bill. The number of clients times the fee charged equals the income earned. The number of shots given times the cost per shot equals the cost for shots given. All of these produce results if you know or can estimate the multiplicand. There are a series of methods that are termed time series methods. The name comes from having past behavior predicting the future, with time as the key change. It's best to keep in mind several key assumptions in the use of time series forecasting methods. This group of techniques assumes that the past will persist into the future and that any changes in the data recur regularly and will continue into the future as well. The data itself must be valid, that is, it accurately describes the real situation. And the data must be reliable, in that others could replicate the results if they use the same data and technique. As we mentioned earlier, you need to have a clean and consistent time series of data that has been cleaned of changes, such as an increase of fees that could mask the reason for an increase of revenue instead of it being the result of more people getting the service. A fundamental problem with the time series method is that it cannot detect a turning point. It's similar to walking in a straight line and expecting to continue, but coming up to someone who just stepped into that spot, making you turn away at the last second. A time series cannot detect that new obstacle. As you work on the various forecasting methods, remember that they can work for monetary units, as in the budget, as well as number counts, such as inventory count or customer counts. Constant change is one method that relies on a trend. Say you have 2 months of data, 190 last month and 200 this month. You want to forecast the next month. You can take the percentage change by dividing the newest number, 200, by the oldest number, 190, then subtract 1, and convert it to a percentage by multiplying by 100. The result is a change of 5.26%. Now, take that change rate of 5.26% and multiply it by the current month of 200 to get 10.52, and add it to the 200 to get the forecast for the next month of 210.52. Another time series method is a moving average. The goal is to smooth the trend line out of the ups and downs of yearly percentage change. A 2-month moving average is shown, but it could be 3 months, 10 months, 30 months, or any number depending upon the length of the time series and the value gained by smoothing it over a longer period. To get to the May forecast using a 2-month moving average, you only need to look at the March and April numbers of 107 and 104. Add them together and divide by 2 to get an average of 105.50. This is your May forecast. A weighted moving average says that the equal weights used in the prior method is not as valuable as assigning different weights to the prior periods. Perhaps you consider April's results to be more indicative of what May will bring, so you give April a 40% weight, while assigning a 30% weight to March, a 20% weight to February, and only a 10% weight to January. Of course, these are just hypothetical weights in this example. To come up with the weights you want to use, you'd need to know more about your data series and what's been driving the monthly results. Weights are usually selected based upon experience and judgment. Although it does not have to be this way, usually the more recent period gets the highest weight, and all weights should add up to 100%. Another time series method is to compute the compound annual growth rate for the time series, and then use that rate to make a forecast. Suppose we had a series with 4 annual amounts, and we wanted to forecast the next 2 years. First, we compute the compound annual growth rate. The factors we use are the oldest number of 100 and the most recent number of 104. There are 3 changes, from year A to B, from year B to C, and from year C to D. A common mistake is to assign 4 because that is the number of time points. But we're not concerned with time points, but rather changes, so it's only 3 changes. The formula we use is 104 divided by 100. It's then raised to 1 divided by n power, n being the number of changes, or in this case 1 divided by 3, and then minus 1 from that result. You then multiply the result by 100 to convert it to a percentage. The result is that, in this example, the compound annual growth rate is 1.32%, from 100 in year A to 104 in year D. We can now use that 1.32% compounding rate as an input to the compound interest rate formula, which is the present value times 1 plus the rate raised to the n power. To determine the forecasted future value for 1 year out, or year E, we plug in the numbers. The present value for year D is 104, times 1, plus the compound interest rate we just calculated, which is 1.32%, or restated as 0.0132 raised to the n of 1, produces the forecast of 105.37 for year E. If we want to project out further, we can use the same inputs but raise it to the power of 2 to produce a forecast for 2 periods out, or through year F, of 106.76. Let me try to demystify something here. We use the wording of raising to the power of. What does that mean? It's a mathematical operation called exponentiation. The n means the repeated multiplication of the base number. So, in doing the future value calculation, you add 1 to 0.0132, then multiply by 104, and then raise to the power of 1 over n. That means that you take the product of 104 divided by 100, or 1.04 times 1.0132 times 1, to finally get 105.3728. For the second year out, it is 1 plus 0.0132, or 1.0132 times itself, to get 1.026574. Then times 104 to get 106.7637. What if you have a forecast total of 1,100 for the next year, but want to divide it into quarters? The simplest approach is to just divide by 4 to get the average quarterly amount of 275. But there may be seasonal differences that you should take into account. Seasonal differences in service delivery may be something like spikes in clients visiting during certain times of the year. Maybe harvest is over, so they have more time to travel to the nearest clinic to receive services. The solution to dealing with seasonal differences is to divide the prior year's quarterly amount, say the 200 in spring, by the average quarterly amount for the prior year, or 250, to produce a seasonal factor of 0.8. This means that the spring quarter is 80% of the quarterly average. You would multiply that 0.8 by the forecast average of 275 to get a seasonally adjusted spring forecast of 220. Simply continue that process to adjust your next year's forecast for the remaining 3 seasons of summer, fall, and winter. Of course, you can use the same method not just for quarters of a year, but also for monthly periods, or for some other frequency that you think is important to use in forecasting, which needs to address seasonal differences. The prior methods were all based on a continuation of trend lines with only a change of time. There are many other methods, but they rely on sophisticated modeling. Such models are built on a theory of linkages between multiple variables, such as economic, demographic, or sociological characteristics that cause a particular dependent variable such as revenues. Regression analysis is the cornerstone of causal modeling, but that discussion is a topic beyond the scope of the current module. This slide illustrates the complicated nature of causal modeling, such as predicting the HIV prevalence rate. Various socio-economic variables, such as the economy and population, represent environmental influences. Additionally, there are numerous socio-cultural value variables, such as risky behavior, that indicate behaviors of influence. All of these impact epidemiological variables that predict HIV prevalence rates. Larger and more complicated organizations conduct causal modeling to fine-tune their forecasts. Budgets are built on forecasts and estimates, so the real value derives from the accuracy of the results. There are ethical issues to consider, though. It's not appropriate to intentionally underestimate revenues as a means of creating an expected end-of-year surplus or an emergency savings fund. Underestimating the spending is just as bad as overestimating it. In government, it's not ethical for an unelected forecaster to limit the policy options of elected officials. Rather, give elected officials and managers the assumptions and caveats used to make the forecast, and even tell them the confidence that you have in the forecast, so that they can then make the final decision on what forecast to use. As in most things, we can learn from our mistakes. The goal is to improve our forecasting ability over time.